Hello, welcome to Security, Cryptography, whatever. I am Deirdre. We're here with co-host David. How are you doing, David?
I'm doing well today, thank you.
That's great. And we also have co-host Thomas. How are you doing, Thomas?
Is that my title? I'm a co-host?
I don't know. You're Thomas Ptacek.
Thomas,
Is that
I had
right?
someone come up to me the other day and be like, your podcast is great, but Thomas keeps talking about how he's bad at his job every episode. He could just not do it.
And our special guest today is fellow isogynist Sophie Schmieg, who is a high-level muckety-muck cryptographer at the big Google. Hi, Sophie. Welcome.
Hi. Yeah, I'm happy to be here. I'm not that high level, I think, but I guess I'm in charge of my team these days. So
That's pretty. You're in charge of other cryptographers.
I'm in charge of other cryptographers. That's true. That makes me like a meta cryptographer.
Yes. You're also, I think you're the first person I met who calls themselves an algebraic geometer. What is an algebraic geometer, if you can define it?
I mean, there is distinct from cryptography. There is the mathematical study of algebraic geometry, and I somehow managed to write a PhD thesis in that study, and the thesis has an introduction that I read the other day and noticed that I talk a lot about elliptic curves in that introduction without mentioning cryptography at all. So it's going to mostly talk about like elliptic curves over the complex numbers and stuff like that. So it's like you can do a lot of basically algebraic geometry is a giant field and cryptography is using like a tiny bit of it.
Yes. Cool. So you're almost a mathematician, algebraic geometer first, and the cryptographer flows from that.
I used to be a mathematician first, and these days I would say I'm probably more for cryptographer.
Fair enough. Chronologically, at least.
Dave, I too am an algebraic geometer, but I'm very bad at my job, so I'm a very bad algebraic geometer.
Thank you, Sophie. I'm Googling your thesis now because I realized that I hadn't read it, so I'm going to go find it and read it.
It's not going to be a fun experience.
I've read other PhD theses that were farther outside my wheelhouse, and I just did it anyway. Beyond being a favorite isogynist and algebraic geometer, you work on some of the things at Google, like the Tink library, and beyond being like a nice to use crypto encryption library with a nice template. One of the things that you worked on that kind of is touching on Tink is binding properties of key material to the key material itself, as opposed to it kind of being defined by a standard or out of band or stored somewhere else. And I think this was like a security design property that I first heard about from you and your work and your team's work related to Tink. Can you tell us a little bit more about that?
Yeah. I have to admit, I didn't come up with this idea. That was done before I even joined the team. It's sort of a combination of things that we've learned between different versions that we had of that eventually led to Tink. Of a lot of problems stem from the fact that when we talk about keys, we think about the 32 or 16 raw bytes of random data that don't include the full information of how it's going to be used.
Yeah.
And the right way, in my opinion, to handle these things is to always consider the key as the entirety of the function or functions that it defines. That it I should be able, just given the key, I should be able to encrypt something. I shouldn't need any additional context for that.
Okay.
And that means I need to know, do I use AES GCM with this key? Do I use AES CTR, HMAC or something with that key? And this is a fairly simple concept in some aspects. I just put everything into the key And then I get a very straightforward API where I just have a function called encrypt that takes a plain text and some associated data and then just encrypts that because the key already includes everything else that you need to know. But it also has a lot of security benefits to it. Like, I usually do not want to use the same raw key material in two different independent contexts.
Yep.
And that means I don't want to use the same key material with two different algorithms. Like the only case where that would be different is if these algorithms are somehow related, like public key cryptography. I have obviously two algorithms that are different but are related. But by like having all that is necessary to know about your problem contained in that key, you get a lot of things that are like common problems automatically. Like we have the problem that you don't know which algorithm to use, or you might put that algorithm otherwise into the ciphertext as like JWT, which is like a favorite topic on this podcast, as I hear. Famously does, where you have like an algorithm in the ciphertext or in the signature, and that means that this isn't trusted information, so it can be changed. And that clearly shows that like this kind of parameter set needs to be trusted. It doesn't need to be secret. It could be just authenticated, but in practice, it's fairly hard to actually enforce that in a generic sense. So just putting everything in one blob and encrypting it with some authenticated encryption will mean that like people will take care of handling the key material securely most of the time, at least. And if we also put the algorithm information in that blob, then they will not make that mistake of putting that information in the ciphertext. It makes it possible to give people an API that is much simpler because it doesn't require them to know what an IV is. It doesn't require them to know what the difference is between various algorithms and trade-offs and so on. So that is where this comes from. And it has a lot of interesting ramifications as well. Like you can switch between algorithms. Like say I want to do a post-quantum transition to, I don't know if isogenies or not, but in any case, I will need to at some point replace my current key with a new key. Yep. And in that transition period, I will have two keys. And if both of these keys are like using the same API to be used with them, which in the case of Tink is what happens. Tink like operates on sets of keys, and the keys could both be like a digital signature or hybrid encryption or something like that. They just have to be the same primitive. And then you automatically can like switch from I'm now using this key as primary to like create my new signatures or to encrypt things or something like that. And use all of these keys as like secondary keys as active keys to decrypt something or verify a signature. And then I can just like I put a new key into that set to like start with things so that it can get distributed. I can switch that to active so that like people start using it. Yes. And then I can like remove the old one once I'm done. And then I've switched the algorithm, and ideally none of your callers and users have ever noticed anything happening at all. Yes, the code changes involved are minimal at best, and it's just sort of like tweaking a pointer or whatever to primary versus secondary and then switching them out. And the API call is the same, which is very nice. It occurs to me, my first thought was like, if you're hard coding parameters somewhere and you only have one parameter set, this is basically not an issue. But you almost always have more than one parameter set, or in the case of JWT or something similar, you have either signing or some sort of like macking or something other than asymmetric. You have something symmetric. You have two different modes. So anywhere where you have a different way to use a key, quote unquote, a key, you will run into this issue. Yeah. And you definitely don't run into this issue if you hard code the algorithm choice. Like that is a way of avoiding a lot of these problems with like trusting like the ciphertext. So like developers will not know what to do with these things, so they will put them into some configuration, and if you're lucky, this configuration is part of your source. And if you're unlucky, this configuration is part of your ciphertext. But by hard coding solves this kind of problem. It doesn't solve the problem of what do you do if you messed up and you need to change something, whether it's like you discovered that your algorithm is broken, or you discover that your algorithm isn't as performant as it could be, or whether it is something like, I need to transition to post-quantum crypto. So you don't really have the ability to switch if you hard code. And that is, I think, the main downside of hard coding it.
That's interesting, because my first instinct would be, if I need to make a change, like with my algorithm or what kind of keys or what mode that I'm running in, even probably not mode, but definitely algorithm, I would want to version. I would want to make a new release of either my software, or like if I'm running a web service or something like that, like I would version the web service to be like, cool, you must upgrade to the new version, whatever that looks like for your software, to do the new cryptographic thing that is either like new signature algorithm or new symmetric matching algorithm or whatever it is. So do you think that you would not have to do that in sort of this kind of Tink API world?
Ideally, you would not have to version. The thing that is important, though, is that you have to operate on key sets when you do these things.
Okay.
And you have to keep in mind that any key in that key set is equivalent. So if I say something is broken and I need to switch, then only good once I'm actually gotten rid of this key, because my key set is only as trustworthy as the least trustworthy key that is
Got it.
That is the main caveat. But like, then you can basically say the key set is your versioning.
Yep.
And it's just pushing it out.
That makes sense. So that instead of it kind of pushing it onto your users to be like, sorry, you must upgrade to get the new thing, it's you controlling the viable key set and being like, cool, shunting all the old keys, but the whole set must be kind of turned over, and then the next algorithm, then that's all you do. You turn over all the keys in the key set and you're done. All right. All right. Cool.
What about the case where like keys have just completely different operations? Like, could you have a key set that's like an X25519 key that's only doing key agreement, and an ED25519 key that's only signing? Like, how do you handle that situation?
That is going to just lead to exceptions being thrown. Like I think the right thing to do there is to say, like, there are these primitives, and we can look up in Dan Bonnet's book how they're defined, and that is what we will use there. And if you like mix those primitives, you're not in for a good time. Like, you don't want to mix a signature scheme with a MAC scheme, because the guarantees that you get are very different. So like, the thing that Tink does is it will have these primitive, or it has these primitive interfaces, and like they basically have like one or two functions in them that are like encrypt or sign or verify or something like that. And then they have a very, very long comment that describes the contract that is pretty much the like academic definition of these functions as like you would define them in a paper or in a book. And that means that you cannot really mix those two. Like when you do that, it doesn't really make sense, because the key set is supposed to be like, from a user's perspective, the keys in a key set are supposed to be sort of, it's not supposed to matter which one they take. Like, they shouldn't even notice, and they notice when they use like an encryption key or a signatures key. And I think that is another one of the mistakes in JWT, in my opinion, that you shouldn't have two things like symmetric and asymmetric signatures are different enough that they shouldn't be in the same functionality.
And I have a little bugbear of whenever a symmetric signature is not really a thing in my mind. A signature is a thing that asymmetric keys are used for. A MAC, a message authentication code, that uses symmetric stuff in its construction. So I call it a MAC or something like that. But I completely understand where people don't see the difference, especially when they're side by side in something like JWT and they're just like...
Yeah, I mean, they look very similar. Like the thing that you will see in Tink is very different is that the MAC interface has the compute MAC and verify function, as they're called, in a single interface, whereas digital signature will have different primitives for signing and verifying because these operate on different keys. Like one operates on the private key, other one operates on the public key. And what's even more interesting is that sometimes even the same algorithm can be a different primitive. When we are talking about MACs in particular, like probably at least half of the time, if not more, when you use HMAC, you're actually using a PRF. You're using it as like a pseudo-random function, as a keyed hash function. And what Tink will do is it has different primitives for PRF and for MAC, and they even use different key types. You cannot use your MAC key as a PRF key because these are, again, completely separate things. They shouldn't be crossed.
Big fan of strong typing in these scenarios, and especially languages that let you do this. I know that Tink is available in Java, in Go. There's like a Rust port. There are some other ones, right?
So we're currently available and supporting C++, Go, Java, and Python. We do have a JavaScript/TypeScript implementation. I don't think that the open source version of that is very usable at the moment. We have, I think, an Objective-C one where it's like similar. We maintain it, but it's not super easy. Like our team only has a finite number of people, and adding a language is a huge difficulty. And like the Rust port is not maintained by us, but as far as I know, there's someone
Project
working on
Oak people. They started the port or something like that. I see Rust, I go there first, even if it's not supported. If it's just over here in a corner, just be like, don't look at me.
If you were
Dave, you go.
Oh no, I had nothing useful to say. Go ahead.
I was going to ask a question, right? Which would just be, this is actually my big Tink question, right? So I guess first of all, like, this is like classic us, but like we dove right into it. No, it's great. I think it's become our trademark, right? But like, it's probably worth asking Sophie to sell the rest of the world on Tink and what Tink is.
So you work on Tink.
I have like and then I have a more specific question about when and how to use Tink, right? But like, my horrible take on Tink, and I've talked to people that were working on Tink before. I know Ty pretty well. Like, to me, it seems like Tink is like Google's answer to Sodium and Tweetnacle, right? Like high-level cryptography library, like kind of a pin-compatible one-for-one kind of replacement. Like different kind of design ideas, right? But the same general goal. Is that a terrible way to think about what Tink is going for?
I don't think it's a terrible way of thinking what Tink is going for. If I would describe Tink, it's like basically like the usual blurb that I give people who are especially interested in joining a team or something like that is that our team started out doing security reviews, and when you do security reviews, you start seeing patterns at some point. Like you start seeing people like going for deterministic IVs when there's no reason to, or they like need to build an AEAD and or like they need to handle their key, and at some point, reviewing the same mistake over and over again is very frustrating, and you just start writing you start writing code that if used will just make it so that is not a problem that you run into anymore. And that is like the main origin story of Tink in a lot of ways, that it's like it makes reviewing cryptographic applications, cryptographic launches much easier, because we can focus much more on the design of like, I want to encrypt this with that key over here and push that data over there and so on. And we don't need to like focus that much on like, hey, how are you generating your IVs? Hey, is there an HMAC on that CTR mode here and stuff like that. So that was the like origin story in a lot of ways. And you've brought up Knuckle and Lipsodium and so on. There is a lot of similarities in like trying to be a cryptographic language that is a cryptographic library that is like hard to misuse and easy to use. I would say the main difference between Tink and Lipsodium is that Tink integrates much more closely with the key management layer.
Yeah.
Like Lipsodium still pushes the like onus on generating, well, it does generate keys, but of like handling keys much more to the user, where Tink tries to, as much as possible, just ideally you would never ever see the key in an unencrypted fashion anywhere.
Nice.
And yeah, I think that is also where like this difference that we talked about earlier is like what do we just hard code the algorithm, or do we have it in the key material itself? Comes in a lot, where when you put it in the key material itself, you can actually do all that key management layer for them. There is like Google's internal key management system has integration with Tink that it will just generate the keys for you, and ideally you get the situation where no human ever has seen this cryptographic key anywhere. And
I love that.
Lipsodium, while it tries to do this, to solve a similar thing, it has a very different approach to it, I would say.
Mm-hmm.
It's a little. It feels a little tricky to me. I've looked a little bit at Tink, and like every other programmer, I've used Lipsodium for things. But like the sort of the design that you're talking about for Tink, it's similar in some ways to how the old Java APIs for crypto used to work with like Java Key Store or whatever it was called. Like the keys are abstracted. You don't ever really directly touch them. The things you do with keys are properties of the key objects. And I don't think that fell out of good crypto design in Java. I think it fell out of everything is an object in Java, and that's just a nice way to stuff it all together, right? But it's a thing that frustrated programmers that were working on cryptography. And one of the advantages that Sodium has is that like it's the wrong way to think about keys. Like, you know, a 32-byte blob is, you know, a curve 25519 key or whatever. Like, that's not the right way to think about it, but it is the easy way to think about it, right? Like, it's definitely, like, if you're just trying to get a system up and running and you know enough to be dangerous, it's an easy way to make a system work. And, like, there's good reasons for you to make this difficult. Actually, there's good reasons to make all of cryptography difficult, right? But, like, yeah, you can imagine that being like one of the things about like, you know, one of the culture shock things about switching from Sodium to Tink. I guess like the biggest question I would have immediately about Tink is we have a lot of Go code and we have a lot of Rust code, right? Like, would you imagine, like, would it be worth spending a lot of time trying to get Tink working or compatible with a Rust code base right now? I imagine you wouldn't be using the Rust port, right? You'd probably be calling into,
would imagine you would call into the C++ bindings, or like the problem really is if you don't have support in a language, you can do two things. You can do the way like I just want something that is compatible, which basically means you look at the wire format documentation and write something that will just be compatible. There is a huge problem though, because it's a Google library, so of course we use Proto in it, and we regret it ever since. But like the Tink keys are fairly awkward to parse if you don't have a good Proto library available. And that has been a bit of a sore spot that we like, especially this year, want to tackle and refactor some things to make it easier to import and export keys, because in some sense, yes, a 32-byte key is the wrong way to think about it. But if I want to be compatible with someone else and I want to transfer my public key and they're not using Tink, then I need to like have something where we can agree on that this is the key format that we're using. And like Tink tries to be very standard compatible usually. Like it will, like we now added HPKE support, for example, because we were like, yeah, we want to have the standard ECIES now that it exists as well. But we obviously need some way of like actually importing the public keys and so on. And that is something that we're working on. It's not trivial because at the same time, we want to make it clear to developers that they cannot just take a key and abstract the parameters from it. Like these parameters need to stay with this key, even if you don't like serialize them with the key. Then you need to like know these parameters and give them back when you want to make them into a deserialized key again, because otherwise you run into that issue of like not knowing where the parameters came from.
I guess like another interesting thing about Tink, like I think like when like libsodium is a derivative of NACL, which was Peter Schwab and Daniel Bernstein and I think Tanya Lange and all them. So like there was an original specification for NACL. Part of the well, sort of, right? But like part of the idea of it was there was a specific set of kind of hard-coded choices for what the algorithms were. And that was part of the premise, right? Is we're taking away lots of choices from people on purpose. So you only make good choices, right? So there's a kind of like, if you tell me that you're using libsodium, it's no longer the case. Libsodium has become its own big thing, right? But you know, if you tell me you're using libsodium, I'm going to assume that you're using some chop poly, variant and curve 25519. And that's not necessarily the case with Tink, and it never really was, right? Like the first thing that ever struck me when people showed me Tink was that it does EAX mode as one of its AADs, right? Which is it's an idiosyncratic choice, right? Like it's the only place you ever see EAX.
It is in Tink, and it is in a certain very important Google infrastructure, which is why it is in Tink. EAX mode. It's an interesting mode, honestly. It's like it's not a bad mode in a lot of ways. I somewhat dislike the fact that it uses the same AES key for both authentication and encryption, and that if you read the paper, then it will be like, okay, now we do a case by case analysis of 56 cases or something like that, which definitely isn't my the best idea, but it is a very nice, very decently fast mode. It's nowhere near GCM, but it is decently fast. And it has a very small code footprint, which I think is the reason that originally people went for it, because you need AES and you don't need anything else. That is how why that mode came in there, because it was used and we needed it for some things. But the largest thing is that it's somewhat hard to give an official default for encryption. Like for the longest time, the predecessor of Tink had the encoded default for AEDs to be AES CBC HMAC SHA-1, which is a completely fine, secure AED. It's not what anybody would use today because it's slow. It uses SHA-1, and yes, HMAC SHA-1 isn't broken, but do we really need more things that use SHA-1? But by it having a default, it makes it very, very hard to actually move away from that default, because as Deirdre said earlier, you need to make a basically breaking version change. And that is very hard if you want to do it across several products at once or something like that. So having the flexibility to choose between different AADs is very useful if you one day wake up and don't like your default choices anymore all that much. And the currently most used algorithms are they all have benefits and drawbacks, and any of them are secure. Like, we can just not pay attention to what people choose, and it will likely be fine. But there's like AES-GCM, which is by far the fastest mode, but it is also by far the most fragile mode. But there's AES-GCM SIV, which is pretty much about as fast as AES-GCM, but good luck finding any support for it in anything that isn't boring SSL. Then there is, EAX mode is like usually just historically useful. There's CTR-HMAC mode, which is the like sort of standard in it is extremely slow because no system can evaluate SHA-2 quickly because there's no hardware support for it in most systems. But it has very good bounds, and it will, even if you violate the bounds, maybe an attacker gets 2 random plain texts. That's not the end of the world, as opposed to like GCM, where they like get part of the key. And then there's like the modes that are like, I don't want to ever think about how many encrypt calls I'm ever making, like XChatter or AES-GCM SIV also falls under that, where you can just be like, when you talk to a team in a review, they will be, you will ask them, so how many encrypt calls do you do? And you get an answer that is either like, so I guess like, let's see, 1, 2, maybe 100 a month, or you get something where they're like, yes, so it's about 1 million queries per second. So about that. And I don't know, don't quote me on that, whether it's actually 1 million queries per second or like, but like definitely
large.
You have a huge range of how many queries people make. And sometimes you want to be like, okay, I give you this thing that is like definitely not going to break if you do that. Or I can just say like, yeah, use AES-GCM. That will give you the least trouble in any interoperability. Everybody supports AES-GCM. And if you're doing like 100 encrypt calls a month, who cares?
Yes.
And like the reason that we care about the number of encryption calls here is because of the nonces, right? It's because all of these AADs are non-deterministic. They're randomized with, a nonce.
Yes.
And the GCM nonce is too small. It's just too small, right? So like the way people like, is that the way you think about the GCM nonce? Is it's a bound on the number of times you can call encryption? I have a weird way of looking at this, which is like, I'm really only interested in these systems to the extent that I can look at code and spot vulnerabilities in them. And like, I don't, like, when I'm thinking about vulnerability research, I'm never thinking about the number of times something's called like as an encryption function. Because even though that system blows up if you encrypt too many times, it's a nightmare pain in the ass to try and like come up with an exploit for that, right? But like, if you were trying to do a deterministic GCM nonce where like you use the nonce 1 first and then you try to make sure that you never use it again, then you use the nonce 2 and the nonce 3 or whatever, like that avoids that like how many times am I calling it bound problem, but it introduces like a whole playground of fun issues for me as a vulnerability researcher, right?
Tink will not give you the option of using a deterministic nonce for exactly that reason. Like you can avoid this issue of like I can only make 2 to the 32 encrypt calls, but I pay for that with. If I have any kind of problems in my state management, I now have a vulnerability that is much, much easier to exploit than that. And like, even with the 2 to the 32, you need to keep in mind that is like the number that the NIST standard mentions for the probability going above 1 in 4 billion. So it's not like I encrypt 4 billion times and here's the key. It's I encrypt 4 billion times and there's a 1 in 4 billion chance that I can recover the key. You need to go like 2 to the 48 or something to get an actual like decent chance as an attacker to like actually do something with it. There's like sort of 2 reasons to still care about it at least a little bit. One is compliance. Like there are some rules that say you're not allowed to. So you need to care about it. And the other is that in some cases, these encrypted blobs sit right next to each other in a database. We added encryption support to BigQuery the other day, and like if there is anything where you can exploit this, then probably the SQL variant is one of them, where you can like just do a nice little query to find if there is any of them. And in the end, it's not that much data to go over. It's only in the like gigabytes, terabytes range. But yeah, it's not really like, I'm not too worried about this being actually exploited for the most part. It's like, I think the biggest worry that I have really is like compliance and best practices and security posture. You should keep an eye on that.
Mm-hmm.
The documentation for GCM and libsodium has a snarky warning at the top saying, GCM super popular, but it sucks. Don't use it, right? But like their approach to this, the whole problem here is it's similar to how they handle keys, right? It's like the interface takes a nonce
with
a fixed size, and it's like, have fun. It's a long-standing like NACL and sodium criticism is like it defers nonces to. It's like the one thing that is going to blow up in these systems is user specified. I should know this off the top of my head, but like remind me the Tink API for AEDs that addresses this.
Have an encrypt and a decrypt function, and it will just not take a nonce. It will only use random nonces. And it will then just, like the ciphertext format is like nonce followed by ciphertext followed by tag. And that way you just completely circumvent that problem because users never can specify a nonce. What we have is something called deterministic AED, which some people don't know about that primitive existing at all sometimes. There is some research on how you can do deterministic authenticated encryption. Like there is the whole like things about like nonce reuse resistant crypto or encryption, and like the various SIV modes where AES, GCM, SIV, I wouldn't reuse the nonce too much because it's still GCM under the hood in the end, or similar to GCM. But like there is AES, SIV, CMAC, I think it's called, where funnily enough, what you need to do is you need to do a MAC then encrypt instead of the other way around. But you compute the CMAC of your plaintext, use that CMAC as an IV, and then use that IV with a different key in CTR mode. And then when you decrypt in CTR mode, we compute that CMAC, see if it is equivalent to your tag or /IV, which is the same thing, and only give the plaintext you recovered once you've verified that to the caller. And because CTR mode is like constant time and will never fail, it can decrypt any string that you give it. That is secure because you don't have any kind of operation on untrusted data that actually depends on the plaintext in any way. It's just XORing with something. And like Tink separates out the deterministic AED from the non-deterministic AEDs, and we try to get people to use non-deterministic ones, and like it's like called AED and not anything more complicated. But sometimes you need to have something deterministic, and in those cases, that mode is very much feasible and very robust against any of like nonce we use, because like say you put a timestamp or something in there or some other fairly weak nonce, as long as your plaintext differs in a single bit, it will be completely different, because the first thing that it does is it takes your plaintext and max it with like a CMAC, which acts as a PRF for the IV. And that means that you can use it with a weak nonce, you can use it without a nonce and get something where you can do like a form of homomorphic encryption that is sort of the most boring homomorphic encryption ever imagined, where the only thing that I can do is like check equality on the outputs.
Hey.
It is homomorphic.
Yeah. You map the plain text and you're using that as your IV. So how is this secure against a chosen plain text attack? I'm probably missing it.
You need to have a different game. It's not an AED anymore.
I see. Okay.
So the game that you play, like the other name that you can call it is pseudo-random injection.
Okay.
Where the pseudo-random function, standard primitive, pseudo-random permutation being the block cipher, and a pseudo-random injection is where the permutation is between sets of equal size. The injection is one set is smaller than the other, and the image of my encryption operation is somewhat sparse in my set, so I can still tell whether or not this was a valid plain text. But I have the same property of like the PRF Oracle description that like I'm not allowed to ask for the same plain text twice, or like I'm expected that I get the same ciphertext when I ask for the same plain text twice. And that is how you define the properties for deterministic AAD. But that is also showing why we make it a different primitive, because it has a different definition. So even though it has an encrypt and a decrypt and they take the same arguments, it will be a different primitive because it violates the contract that you make with an AAD. With
a classic AAD, yeah. Okay, cool. Thank you.
This is a thing Colin McCarthy talks about a lot. Like if you bring up SIV with him on Twitter, you'll get a long thread about how like there are applications where deterministic AADs are problematic because of message correlation, because like they're not randomized.
Deterministic AADs is definitely a bit of a sharper tool. Like it is something that you need in quite a few scenarios. You need something where I can still have equality, but it also means that there is, if I like take a text and tokenize every word and encrypt it deterministically, I can totally do some statistical attacks and probably recover several words at least there. So SIV has its place, but it shouldn't be your go-to when you want to encrypt something.
Mm-hmm.
You have, in the Tink API, there's also, you have XChaCha. So like my feeling, and again, I'm bad at my job, so David can correct me on my feelings. But like my feeling is that when you're thinking about this problem of, I have to manage this nonce and I have a certain number of calls I can give for a certain nonce size or whatever, like the two kind of standard answers in modern cryptography for that problem are deterministic AEADs, and GCM Civ is the big one that people talk about. And then XChaCha is the other one where the solution to that it provides is just a gigantic freaking nonce, right? Like, just so much that you could just fill it up with random data and never ever think about it, right?
Yeah.
Which I kind of like because it's really simple to reason about. How do you feel about that argument that like, nonce misuse resistance is maybe a little bit of a blind alley?
I definitely like
we really
the
just
fact
need
that
a simpler nonce.
has this long nonce, and I think that the fact that we're still stuck with AES, which with its 16-byte block size, which like kind of limits all of these nonce sizes and everything, is kind of a problem a lot of times because it makes collision probabilities way too low. I think that the use cases are slightly different. Like the question is, do you have something that can act as a nonce, maybe as a low quality nonce, but can act as a nonce, like something like a timestamp is a perfectly reasonable, very low quality nonce. Like, there will be collisions, but there shouldn't be too many collisions. Or do you just not have anything of that sort? And I think that definitely the XChaCha methodology is like the best way of dealing with that problem. The main reason why we have both in there is performance related. Like when you care a lot about the nonce space being exhausted, you're likely making a lot of queries. So the difference between GCM SIV and Exchequer 20 is significant enough to count in these cases to be like enough monetary value that you want to have the option for both. Like just because ASGCM SIV can use all of that nice polynomial arithmetic over characteristic 2 tricks to speed things up, which Exchequer 20 Poly 1305 doesn't have, or it uses AES and has hardware support for that. So it is Exchequer 20 Poly 1305 is certainly not the slowest cipher out there. And it's like the best choice if you're not sure what hardware support platforms have. But if you know that you have hardware support for both the AES part and the carryless multiplication part, then AES GCM SIV is quite a bit faster. And so if you are in a situation where you really care about this non-space, you probably want to use C++ and you probably want to use GCM SIV or Rust, I guess. But we don't have much Rust, unfortunately.
Yeah, it was in my brain. It was ASGCM for all the hardware that supports it, and then Poly for software, the fast option for software that doesn't have the hardware support. And I think that's been burned in there from like TLS 1.3 stuff. And yeah.
That is, as far as I can tell, that is pretty accurate. And then you have anything CTR or CBC HMAC very, very far off the very slow end because
Legacy
HMAC is very slow.
Is Tink the first like thing you did at Google for cryptography? Like, how did you get from algebraic geometer
is actually a very
to
good
where
story
you are now?
because it is not as all straight. So I finished my PhD when I was at 2013. And then I got a job offer from Google 2014 and ended up being on the search ads team, on specifically the team that computes the auction price. Wow. So like the different parts that like all the things that run when you do a search query that like determines what an advertiser will have to pay when you click on that. And I was on that team for 4 years and was then like, oh, okay, I'm kind of looking for something else. Like you can't do search ads forever. I got too bored with that. And I was looking at several different teams, and then I ran into Ty on that search, and Ty was like, wait, you know algebraic geometry? Why aren't you doing crypto? You know this crypto stuff as well. And that's how I ended up doing crypto, or that's how I joined the crypto team. I was doing crypto before then as well, mostly like because I was like doing things like doing a PhD in algebraic geometry, and what usually happens then is that you have to teach the class about cryptography. And I was like, yeah, I kind of want to know how this now actually works. Like, I understand why like, I compute an Euler token and then you get an RSA that works, but that can't possibly be how you actually use it. And so I like sort of doing that PhD on the side was like reading Schneier's book and stuff like that to like at least know how this works. And it turned out that would become very useful later on. But that's how I ended up on the cryptography team, which was like, yeah, it was definitely not the straightest path into it. And it was definitely a case of like not really knowing how to get into cryptography. Like I always was interested in it, but it's a very hard field to get into if you don't happen to be in the right place. And the University of Ulm in Germany was not the right place, at least for me at that time.
I had no idea you worked on search or ads or anything. That's awesome.
Oh yeah.
So Ty, who you're talking about, this is Ty Duan, right? So of TLS Beast and Crime, one of my favorite people on the internet. So Did working with Ty change the way you think about cryptography? Are you like a different kind of cryptographer for being in contact with Ty?
Yeah, definitely. Like
and Ty's team
as
and
I
all
said,
that.
things like the way that Tink handles keys was something that existed before I joined the team, and it's definitely like the interesting part about that is that it very, very quickly sort of gets absorbed as like your default way of thinking about things, to the point that you're like sometimes I'm like incapable of like imagining that a key would not be containing the parameter set, because it's not a complete key. Why would you do that? So it is like, it felt very natural, and like, especially given that I like worked on a more software engineering focused team for like several years, it also makes the interface feel a lot more natural in my opinion, because it's a very clean API of like, when I want to encrypt something, I want to give you the things that I want to encrypt. I don't want to handle unknowns. I don't want to like think about that. So it very, very quickly just sort of like, oh yeah, this is how you're supposed to do that. So yes, definitely it's changed my way of thinking about cryptography. Like almost to the point that I didn't even notice that it changed.
I have a dumb question, right? So like, in kind of the same vein, because when I think about the way Ty thinks about cryptography, it's he comes from vulnerability research too. I've kind of a mental, this is a total aside, but I have like kind of a mental kind of org chart of cryptography. I try to keep track of how many people are in cryptography or doing the kind of cryptography that they do because of the influence of Trevor Perrin. Because you get from Trevor Perrin to Nate Lawson, and then from Nate Lawson, you get to Ty Dwan, and then you get to like all of the modern TL has attacks through the work that he did. Like, I don't know, that like the tendrils of that Trevor Perrin guy are bananas. Somebody asked you how you got to however many followers you have on Twitter. I don't know how many followers you have on Twitter, but your answer was that you dropped a vuln to get them.
Relevant,
what was the vuln?
To the conversation? The vuln was really funny. What happened was that someone imported some AWS SDK into some Google system for some project. I don't even know what project it was. And it tripped some required review alert, I think because it used MD5 somewhere. And it was like the entire AWS SDK. And I like looked at that giant code base and I was like, yeah, I can either just click LGTM, or I can at least say search for crypto, and that's what I did. And that way I managed to find the S3 crypto S3 encryption SDK, which like did several things that we talked about from of like having the parameter set stored with the ciphertext as metadata in the bucket instead of having it stored with key material or otherwise authenticated. And it was that was the biggest one. And like it supported both CBC without an HMAC and GCM mode, and GCM mode was the default. But CBC was in there because of like it allows for an easy streaming API, which is a topic for a different podcast, I think, on the difficulties of doing encrypting large files. But so what you could do is you could take, if you have write access to a bucket that has these encrypted files in it, you could change the algorithm from GCM to CBC, and then you can do a padding oracle attack on the CBC that like requires the entire 16 bytes of plain text to be guessed. It's not the most feasible attack in most cases, but it's definitely feasible in certain cases. And that was like, I think that was the point where I gained the most followers, that I like found an AWS vulnerability, and that like people like that. It's like I like the story because it was just so random. It was just really like me trying to see, like, basically me not wanting to just rubber stamp it and at least look why this alert wanted me to review something, and then finding like, wait, that's not how this is supposed to be.
Why is there MD5 in here?
The MD5 was another part of the vulnerability, unfortunately, because there was the cloud buckets have these E tags that are like used as integrity checks. And what it did was this client computed the MD5 of the plain text and encrypted the plain text, and then added this MD5 of the plain text in plain to the metadata. And that was like, so that was like the third part of that vulnerability of like, yeah, you shouldn't, like, the MD5 of plain text for a cryptographer is the same as the plain text. So congratulations, you just revealed the plain text. And like, yeah, it was all in all, it wasn't the biggest vulnerabilities per se, but they were kind of cool vulnerabilities. And so people enjoyed that.
I love that it got fixed.
Yep. yes. AWS did a stellar job. Like I gave them, like I notified them, and they like fixed it very fast. And they were like, "Oh yeah, this was like, yeah, we didn't really see that part," and we're very happy that they could fix that. And yeah, it definitely got fixed and was nicely. Is working very nicely now.
Awesome. What's happening in Sophie land that's not just all Tink and keys all the time?
Isogenies, yeah.
Isogenies.
We can,
I don't believe they
this
exist.
Isogenies of like, I've been trying to find a way of selecting a random supersingular curve, which is an extremely hard problem.
Yes, it is. And I was going to be like, have you solved this?
No, I'm nowhere near solving it. I think if anything,
oh my God,
I'm getting convinced that it is impossible under certain under certain assumptions. But I'm not. I haven't formalized that enough yet to actually like be like, yeah, it's definitely impossible to do this. But I think there's an argument to be made that it is not possible to select a random supersingular curve without revealing without learning the endomorphism ring.
Yep.
But which is sad. Like it is. Isogeny is the closest that we have to this paradise that are elliptic curve groups for cryptography. And they're just nowhere near, like, they're nowhere near as good as what elliptic curve group structure can do. But
yeah,
at least they are Diffie-Hellman variants, so that's good.
What do you think of the class group actions versus the supersingular walks, the SIDH style?
I've looked a lot more at the supersingular walks than I've looked at the class group action. The class group action, it definitely seems to have a lot of promise. I'm a bit concerned that it has like these abelian things happening. Yeah. Because it feels to me, intuition-wise at least, that quantum computers are bad at anything non-abelian. Yeah. And doing something abelian feels kind of scary. Yeah. On the other hand, the class group is notorious for being super difficult to compute anything with. But then again, quantum computers can compute a lot more about the class group than normal computers can do. Like there's a bunch of cases where the algorithms, when you read like class group algorithms, where it just says, and now we compute the discrete logarithm towards this basis. And you're just like, okay, that means that
that's easy.
I'm not going to use this for cryptography ever, because I'm like restricted to like maybe 10 bits at most.
Yeah, I mostly am just sort of aware of like SIDH and everything related to it is like, oh, we were too conservative. We can reduce our sizes because we were too conservative, and everyone was worried about these auxiliary torsion points being a vulnerability mechanism, and it doesn't really seem to have panned out. But on the other hand, like class groups and Seaside and CRS and stuff like that, it's like, no, we got to keep bumping up the parameter sizes, and we have to keep bringing down the capability of our adversary as opposed to modeling them as like, you know, the most powerful adversary with the quantum computer that might ever be in order to like theoretically be able to deploy this thing. And I'm just like, it's a lot of hedging.
Yeah, that's definitely, I mean, that's like the downside of like all isogeny crypto to some extent a bit, that like compared to lattices and codes, it's very new and it's very scary. Like I talked to my PhD advisors and they've never heard about the fact that people want to do cryptography with that stuff. And they like, we need to be at that point where like any mathematician who works on this topic is aware, if they like right now, if they run into a factorization algorithm, we can be fairly certain that they're like, oh yeah, this is going to break RSA. This is a big deal. I should follow up here. Whereas with isogenies, I'm not sure if they would notice. And we definitely need to get to the point that people notice. We need to like have much more like research and also like making it much more approachable, like understandable for non-algebraic geometers to do before isogenies are really ready to work out. I'm pretty sure what will happen is similar to the way it happened with RSA and elliptic curves, where RSA was there first, and I can teach RSA to a high schooler and they will probably know, like they probably have an idea of why it's difficult and how it works. Elliptic curves is much harder to teach and to understand, but it's like it has clearly shown that it's superior to RSA in almost all ways. And I would be very unsurprised if we see the same thing with the post-quantum algorithms, that like lattices and codes will be the things that NIST goes with now. And then over time, as we understand isogenies better and trust them more, we actually switch to isogenies because we made them faster, and they are smaller and so on. Like same things that happen with elliptic curves.
Yeah, I like that kind of pattern match because that does feel very. There's a ton of stuff you can do with lattices that we probably will never be able to do efficiently with isogeny stuff, like the fully homomorphic encryption and you know whatever. But that pattern of like the first things first gets deployed, it's fine, you know, you can understand it easily, which is a lot of the lattice stuff, and the code stuff goes back so much even further. Yeah. But then when we learn algorithmic tricks and implementation tricks for the isogeny stuff, it's both smaller and faster, and everyone's like, let's use this. This is better for reasons.
Yeah. But I definitely think right now I can't see NIST or anyone like going with isogeny and being like, oh yeah, we totally trust this. It's cool, and I want it to be the one that wins out in the end, but it's not there yet.
Yeah, it's a bit early. And yes, I want all the mathematicians who are just hanging out in their departments being like, wait, you're using this for cryptography? You should know about this thing that we just all vaguely know. We never mentioned it before.
Wasn't almost nobody even like using elliptic curves at all until Wiles showed up and was like, hey, I've proved Fermat's last theorem.
Something like that.
Because it was definitely he made algebraic geometry the hot topic. But elliptic curves are sort of like, you run into them automatically when you do algebraic geometry. Like in some sense, you can say that like Jacobi and Abel worked on elliptic curves. You can't tell them that though, because they wouldn't have known that. But they, like a lot of the theorems that they did are actually theorems about elliptic curves or like related to elliptic curves. They just didn't know that they were doing that. But certainly for use, like it certainly got a lot more popular with Wiles and Fermat's last theorem. There's some other things. So there's like the generalized Riemann hypothesis that you can prove for in algebraic geometry instead of just being like, oh yeah, we conjecture this. And things like that, and like the algebraic number series, like basically Grothendieck started a lot of the like memes in algebraic geometry and made it this very very popular research. It definitely isn't the most well researched for cryptography there.
Yeah. It's so new. Sophie, thank you so much. I'm so glad you could join us. This is great.
One last hot take. Is anyone ever going to prove or disprove the Riemann hypothesis?
Let me see. There has been some progress that has been made so far, at least the things that I did 10 years ago, or like more than 10 years ago when I was still studying this. None of them asymptotically ever moved beyond the z, the real part of z is equal to 1 line. Like they have like proved the Riemann hypothesis for like sort of curvy bits, but they all asymptotically go to the real part being equals to 1. So it's not looking super good. But then again, I don't know. It's more likely to be proven than P equals NP, I think.
I hope so. I hope so. We're all screwed.
I mean, I hope nobody proves P equals NP, but even P unequals NP seems to be one of the things that is very hard to get any traction on.
Spicy hot take. No one's ever going to prove it. Cool.
I mean, maybe it's not provable. Like there's a bunch of things that we've shown that they are undecidable.
Yeah. Sophie Schmieg, thank you so much for joining us.
Yeah, thank you for having me.